All right, today we're going to talk about regression. Regression analysis is one of the most common approaches used in predictive analytics. We use it to capture the relationship between two or more variables and to predict the outcome of a target variable based on one or more input or independent variables. Basically, we like it because it helps us understand the relationship between multiple variables. So linear regression model hypothesizes that the relationship between the response, or y variables, and predictor, or x variables, is linear. In the pictured figure, the diagrams with green lines illustrate linear relationships. The diagrams with the orange lines illustrate nonlinear relationships. Linear regression is a common first choice for analysts and investigators, but it's important to note that not all relationships are linear. For example, the level of responsibility you have as a person throughout your life. You don't have a lot of it, and then maybe as a teenager you get a little bit more, and then the day you turn 18 you get a lot more, and then a little more at 21, a little more at 25, and basically, unless you have a whole gaggle of kids, 25 is kind of where it peaks. And just a couple of real-life examples illustrating linear and nonlinear relationships. Chart 1 illustrates a linear relationship. It is the mean daily nurses per shift on a hospital ward and the adjusted mean daily number of patients on that ward. It looks like that as patient census increases, so does the staffing. And, well, we really would like to hope that is accurate. Our second chart illustrates a nonlinear relationship. This chart illustrates fuel economy for 4 different types of vehicles: Toyota Prius, Honda Civic, BMW 328i, and the Subaru Outback. And while these are all cars, they're fairly different, the Prius being a hybrid, and the 328i and Outback having somewhat larger engines than the Civic. But we see that they all seem to have a very similar relationship when it comes to fuel economy, and that is it improves with speed up to a point, but then once you hit about 60 miles an hour, fuel economy tends to drop as speed increases. And it would be difficult to express this relationship accurately with a straight line, especially when we look at the Toyota Prius and the Honda Civic. Those are very, very non-linear. And if we tried to approximate it with a linear relationship, it probably wouldn't fit very well. So a few notes on the variables we'd like to use in linear regression models. First, they must be expressed in or capable of numerical expression. That numerical expression must also be meaningful or interpretable, and sometimes that can be tricky, especially when we're working with, well, categorical variables. Categorical variables reflect categories, so they can be hard to quantify numerically. The most common way we express categorical variables is with a dummy variable, also known as an indicator variable or a binary variable. These variables express 2 categories of a categorical variable. So, on versus off, male versus female. Sometimes they're denoted in equations with a lowercase letter d, but they're still either a dependent or an independent or an x or a y variable. So sometimes if you see a variable denoted as a lowercase d, that's what it means, but you will not always see binary or dummy variables indicated with that lowercase d. That's just a little heads up. So in a simple linear regression model, we only use one predictor variable. We always only have one dependent or response variable, that's our y variable, but we can have multiple predictor or independent variables, those are our x's. So in simple linear regression, we have one of each. We have one dependent or y variable, and we have one independent or x variable. And the model is expressed as the dependent variable being predicted by beta naught, which is the intercept. So that is the value of y when x is equal to 0. Beta 1 is the slope of the regression line. And then we have an error term that captures sort of the randomness, the differences between our observed variables and the values predicted by our regression line. And we can even see here we have our intercept. So when x is equal to 0, our regression line crosses the y-axis here at about 10. So that's going to be our beta naught or b naught, which is our predicted value of the beta. And then the blue line is our regression line, and that is the line that is expressed by this equation. This being our intercept and beta 1 being our slope. And then we can see that our error term is calculated from the difference between our observed values, which are these black spots, and the corresponding position on the regression line. So this diagram illustrates it with a little bit more clarity, where you can see the regression line and then how we calculate the error term from the difference between the actual value of y, which comes from this observation, and the predicted value of y, which is where the line passes closest to that value for y. And then when we're predicting the value of y, when we're estimating our regression line, we put a little hat on y to say that this is an estimate of y. This is not an observed value. This is an estimated value. And that's the critical difference between y without a hat and y with a hat. And then in some notation and some examples that walk through how to do regression by hand, you'll also likely see y with a bar over it, and that's the mean value of y. So y can sometimes wear some different hats, and each one represents a different calculation or element. So linear relationships can be positive, negative, or non-existent. We take all comers. In a positive relationship, as y increases, x also increases. So when beta 1 or b1 is greater than 0, that tells us that that independent variable, that x variable, has a positive relationship with our dependent variable. So if you're ever being asked if something is a positive or a negative relationship, you can always look at the sign of the coefficient for that independent variable. We have negative linear relationships, which are those where as y increases, x decreases. And sometimes there's no relationship. And in these scenarios, our coefficient is usually very close to 0, if not 0 itself. Very few things in regression are perfectly exact, but when we're very close to 0 and you see a very, very flat line, you can often infer that there's no linear relationship. That doesn't mean there's no relationship. That just means that that relationship cannot be expressed linearly. So then we also have multiple linear regression, which is very similar to simple linear regression. The primary difference is that it has more than one predictor or independent or x variable. So while we still only have one dependent or y variable, now we have additional x variables. And it makes a lot of sense because few relationships in this world can be reliably estimated with just one predictor variable. Think about when you got dressed today, or yesterday, or last time you went out. More than one variable influenced your decision. I know for me, usually before I get dressed, I think about what I need to do that day and the weather at a bare minimum. And sometimes other factors are at play, like when was the last time I did laundry? So the model looks very similar, but now we have more betas, more coefficients for more variables, because every predictor variable or x variable has their own coefficient in the model. The biggest challenge we run into when we move into multiple linear regression is that it's no longer as easy to illustrate on a two-dimensional chart. And that's one reason why we really emphasize simple linear regression, so you can visualize the idea that we're using a line to explain a relationship, even if most relationships are more complex than just one variable explaining a dependent variable. And likewise, our equation for y hat is the same as with simple linear regression, just with more betas, one for each of our predictor variables. The error term is still the calculated difference between the observed and predicted values of y. And in fact, as we move into multiple linear regression, the error term becomes even more important because we rely on it to help us ensure we're getting the very, very best model. So we use ordinary least squares, or OLS, to find the sample regression, minimizing the error sum of squares. And this helps us reduce the total error in the model, which enables us to find the very best fit possible to represent the relationship we're investigating.